Before I introduce the complex eigenbasis theorem, I hope you to look at this case, which is a system of two equations. Okay, it's a system with the matrix, 2 by 2 matrix. So here we have X, Y. Okay, so we're trying to solve such a homogeneous system. So again, we have the constant coefficient matrix A. So here is a very simple example to give you some it's kind of a prototype before we develop a general case. So if we have a matrix A, here this A is actually, in order to extend to general system, let's just write our notations in a more standard form, x1, x2, right? So let's see it this way. And then you, this is the system, x prime equals ax. We're very familiar with the system. A is a constant coefficient matrix, and it's a real valued matrix. But if you try to decide its eigenvalues by solving this characteristic polynomial equation, you try to determine eigenvalues of A, we discover that we have complex eigenvalues. Yeah, by solving this, we find lambda, right? So lambda to be found complex values. So we have lambda 1 being 2 plus 5i, and lambda 2 minus 5i, and they are conjugate. Yeah, so complex conjugates. Then let's see, is that a surprise? Actually, whenever you have a real valued matrix, and if you have an eigenvalue and its corresponding eigenvector, suppose the lambda is a complex eigenvalue, V is the corresponding eigenvector. Then you take a conjugate, both sides. And immediately you discover that you see this conjugate of lambda is also an eigenvalue. And its corresponding eigenvector is the V bar. Because for the A is a real valued matrix, so A conjugate is itself. So this shows that whenever lambda V, you see if a V equals lambda V, that means whenever V is an eigenvector corresponding to the complex eigenvalue lambda, then the conjugate of lambda is also eigenvalue, and the corresponding eigenvector is V bar. So that conclusion is to reveal a fact. That means whenever you have one complex eigenvalue, this, for example, in our case, so if you have found one complex eigenvalue, then its conjugate is also a complex eigenvalue. Yeah, just to prove that. And then let's calculate for lambda 1. When the lambda 1 is 2 plus 5i, it's V1, the corresponding eigenvector is 1i. Lambda 2 minus 5i, its corresponding eigenvector, right? One of the eigenvectors corresponding to this lambda 2 is 1 negative I. Yeah, so that is to show just indicated in this. That means whenever lambda is an eigenvalue, then lambda bar, the conjugate of lambda, is also an eigenvalue. When V is the eigenvector corresponding to lambda, then V bar, the conjugate of V, must be the eigenvector corresponding to lambda bar. So this is what we can notice. So this is lambda 1, its eigenvector is 1i. Then lambda 2, the conjugate, has eigenvector 1 negative I. So here is a very simple problem to show that for this A, this real valued matrix A, we find its complex eigenvalues and the corresponding complex eigenvectors. And how do we represent a general solution? So we can simply apply that formula just like how we use e to the lambda 1, right? Although it's a complex value, we can still do that. And times v1, that's a solution, but it's complex valued solution. Yeah. And then e to the lambda 2 is a complex, times v2, that's a second complex valued solution. And then if I want to have a general solution, the vector will be arbitrary combinations of the two, right? So we can put a C1, C2. Yeah, so we can do this, but we don't like using the complex valued functions to represent our general solution. So we want to give a more friendly representation, because right now if we write complex value, we just write E lambda 1, which is 2 plus 5i, that's lambda 1 times t. V1 is 1i. And C2 is, okay, so e to the lambda 2, 2 minus 5i, that's lambda 2 times t. The V2, the corresponding eigenvector is 1 minus I. So the vector. So then we do the arbitrary combination will give a general solution to the homogeneous system here with this coefficient matrix A. Okay, so we have the general solution for the problem, but the solution is complex valued. So our next task is, can we make it more friendly? So let's see if we have a complex valued solution, right? But right now we do have two independent solutions, although they are complex valued, and they are used to generate a general solution. Okay, so, but can we possibly give two real valued solutions and use them to represent general solution? So the answer is yes. So we only, for one complex valued solution, we can write it right? In terms of real part, imaginary part, then we can show that. Yeah, so let's decompose this complex valued solution into two parts. So here is one complex valued solution, and we are going to decompose, we're going to split it. So this, only this part, let's work on first one to see something. So 2 plus 5i, 1i, only that part. So we're going to work on this part to write it into two parts, because we will see, okay, so this e to the 2t, right? So we can write it e to the 2t. And e to the 5i times t. So basically it's a 5t. And there's an imaginary unit, I. And then this 1i. So this part, we want to continue to work on it to see e to the 2t, we keep it as is. But this part, by Euler's formula, we can write it as cosine 5t. Cosine 5t plus I sine 5t. Okay, so that is the identity. We write it in this form so we can easily see imaginary part, and then multiply by 1i. So then you further reduce it, see each, so this quantity, right, should multiply each entry of this vector. So then we get a vector. So 1 times the quantity is cosine 5t plus I sine 5t, because 1 times this quantity. And then I times this quantity. So we still have e to the 2t I. So that is I cosine 5t. I times I will become -1 sine 5t. And then that is as a result of multiplication. So we split the solution, this solution, into a real part and and plus I times some imaginary part. Yes, we can. So the real part clearly is e to the 2t, right? We can take it out. So because that is to every term, so we can simply e to the 2t here. And then the real part is clear. So that and this. So let's put it here. So which is a cosine 5t negative sine 5t. And then we have, so this is the real part. Imaginary part, there's an I, so I put I here. Then times sine 5t and cosine 5t. So now we can see the solution has two parts. And e to the 2t times this, that's the real part. Imaginary part is e to the 2t times this quantity. So we have real and imaginary. So this complex valued solution, if it is a solution, we can prove that for any complex valued solution, right, including this one, if it is a solution of a homogeneous problem, and its a real part and its complex part are also solutions of the problem. So basically, we have found two solutions using this complex valued solution. So let's write out the real part of this complex valued solution is I just copy it so you can see clearly. Yeah, so this is the real part. And the imaginary part of this complex valued solution is, so I'm going to copy this times this, right? That's the imaginary part of this solution. So I will write sine 5t cosine 5t. Okay, so if we don't like this complex valued solution, but we can use it to find two real valued solutions. And they are these two in black font. So then the good thing is that we have found two independent solutions, and we can use this two instead of this two, right? Because we don't like those complex value solutions. So from this one complex value solution, we discovered two real valued independent solutions. So let's use the real and imaginary part of this solution to generate our X, the general solution. So here, the general solution can be represented as x1, x2 equals some arbitrary linear combination. For example, we can call it some constant here, h plus k, another constant. So we can give a general solution in terms of real valued functions, using real valued functions. So that's our general solution for this x. Yeah, solution formula for our system. And then you might wonder, what if I choose, instead of this one, right? What if I choose the other one? So what do I get? So choose the other one. Notice this other one is because of the conjugate. So yes, you can try. Eventually, you will discover the real part, imaginary part of this one would differ only at most by a sign. So that means we still get the essentially same solution set, right? Because if you find the real part, imaginary part, only differ by a sign, then this sign can be also included in this h or k being arbitrary. So then you still get the same solution set. So that will not affect our solution, this general form of the solution. So we can write our general solution in this form. So you see this number 2 is the real part of the eigenvalue. Yeah, because our eigenvalue is 2 plus 5i, 2 minus 5i, right? So the 2, yeah, so it's the real part of the eigenvalue. So the 5 is the imaginary part of the eigenvalue. Yeah, so we can choose 5, but -5 may cause some sign change here, right here, somewhere. So it doesn't matter. You just use the 2 plus 5i, then we use its corresponding eigenvector. We can already get this general solution formula. So this eigenvalue and its conjugate produced this pair of general solutions for the system. And if you understand this problem, then you will be able to understand the complex eigenbasis theorem. So that with this example, and I hope you read from the textbook, the complex eigenbasis theorem to understand, okay, how the generalized version is similar to this simple case.